branch of statistics that allows you to make predictions or inferences from the data that you have gathered from your respondents. With inferential statistics, you take data from samples and make generalizations about a population. Inferential statistics are often used to compare the differences between the treatment groups. It also measures from the sample of subjects in the experiment to compare the treatment groups and make generalizations about the larger populations of subjects. Your inferential statistics needs to have hypothesis testing. Hypothesis testing is common in statistics as a method of making decisions using data. In other words, testing a hypothesis is trying to determine if your observation of some phenomenon is likely to have really occurred based on statistics. According to the San Jose State University Statistics Department, hypothesis testing is one of the most important concepts in statistics because it is how you decide if something really happened, or if certain treatments have possible effects, or if groups differ from each other, or if one variable predicts another. Statistical hypothesis testing, also called confirmatory data analysis, is often used to decide whether experimental results contain enough information to cast out doubt on conventional wisdom. For example, at one time, it was thought that people of certain races or color had inferior intelligence compared to Caucasians. A hypothesis was made that intelligence is not based on a race or color. People of various races, colors, and cultures were given intelligence tests, and the data was analyzed. Statistical hypothesis testing then proved that the results were statistically significant in that the similar measurements of intelligence between races are not merely sample error. Our hypothesis must have these following characteristics in order for it to be considered a good one. It has to be simple, specific, and stated in advance. For example, Tamiflu, an example of oseltamivir, a drug of choice for H1N1, is associated with an increased incidence of acute psychotic manifestations. It is either true or false in the real world. Because the investigator cannot study all people who are at risk, the researcher must have a hypothesis in a sample the target population. No matter how many data a researcher collects, he can never absolutely prove or disprove his hypothesis. Let us simplify it by having an analogy between judge decisions and statistical tests. So, if a judge decision is innocent, the defendant did not commit crime. It is just like stating a null hypothesis, where there is no association between Tamiflu and psychotic manifestation, meaning your Tamiflu is innocent. If the judge decision is guilty, the defendant did commit the crime. And that, on the other hand, is the alternative hypothesis, where there is association between Tamiflu and psychosis. If a judge decision is standard for rejecting innocence beyond a reasonable doubt, it is just like a standard for rejecting null hypothesis with a level of statistical significance. Correct judgment is to convict a criminal. So, the correct inference, on the other hand, is conclude that there is an association when one does exist in the population. Correct judgment, if it's innocent, is to acquit an innocent person. The correct inference from that is to conclude that there is no association between Tamiflu and psychosis, when one does not exist. It's incorrect judgment if a convict or if a judge convicts an innocent person. It is incorrect inference if in statistical tests if one will conclude that there is an association when there is actually none, and you call that a type 1 error. An incorrect judgment from the judge if a judge acquits a criminal. On the other hand, in a statistical test, if there is a conclusion and states that there is no association when there is actually one. So that is called a type 2 error. So incorrect inferences type 1 and type 2 affects the results of the study. These inferences are based from p-value. P-value is the probability of obtaining the study results by chance if the null hypothesis is true. The null hypothesis is rejected in favor of the alternative hypothesis if the p-value is less than alpha and the predetermined level of statistical significance. When you say non-significant result, this refers with p-value greater than alpha. It does not imply that there is no association in the population. They only mean that the association observed in the sample is small compared with what could have been occurred by chance alone. So alpha depends on the significance level and the confidence interval of the study. Usually, it is 0.05 or 5% level of significance, meaning to say there's 5% room for error and 95% you assume that all data 95% is correct and reliable. In clinical studies, we can increase our confidence level or significance level into 1%, which makes our alpha value to 0.01. So if our p-value is 0.05, if it's less than 0.05, our result indicates significant. If it is more than our p-value, which is 0.05, it means our result is non-significant. So the inference will depend on what type of hypothesis you have used, if it's null hypothesis or the alternative hypothesis. Examples of hypothesis tests are parametric tools and non-parametric tools. Parametric statistics or parametric tools is a branch of statistics which assumes that sample data come from a population that can be adequately modeled by probability distribution that has a fixed set of parameters. Conversely, a non-parametric model differs precisely in that the, the parameter set is not fixed and can increase or even decrease if new relevant information is collected. Non-parametric tests don't require that our data follow the normal distribution. So if our data has a skewed distribution, it is a must or it is advisable to use non-parametric tests. They're also known as distribution-free tests and can provide benefits in certain situations. Typically, people who perform statistical hypothesis testing are more comfortable with parametric tests than non-parametric tests. So these are the reasons why we use parametric tests. First, parametric tests can perform well with skewed and non-normal distributions. This may be a surprise, but parametric tests can perform well with continuous data that are non-normal if we satisfy the sample size guidelines. So we really have to determine the correct sample size so we can use parametric tests. Parametric analyzes sample size guidelines for non-normal data. So if we have So if you need to perform one sample t-test, your sample size should be greater than 20. If you need to perform two sample t-tests, each group should be greater than 15 respondents. If you need to perform one-way ANOVA, and if you have 2 to 9 groups, each group should have at least 15 respondents. The second reason why we use parametric tests is it can perform well when the spread of each group is different. While non-parametric tests don't assume that your data follow a normal distribution, they do not have other assumptions that can be hard to meet. For non-parametric tests that compare groups, a common assumption is that the data for all groups must have the same spread. So if your group have a different spread, the non-parametric test might not provide valid results. The third reason for using parametric tests is the statistical power. Parametric tests usually have more statistical power than non-parametric tests. Thus, we are more likely to detect significant effect when one truly exists using parametric tests. On the other hand, non-parametric tests are used for the following reasons. First, your area of study is better represented by the median. For example, the center of the skewed distribution, like income, can be better measured by the median, where 50% are above the median and 50% are below. So if you add a few billionaires to a sample, the mathematical mean increases greatly even though the income for a typical person doesn't change. When your distribution is skewed enough, the mean is strongly affected by changes far out in the distribution's tail, whereas the median continues to more closely reflect the center of the distribution. For these two distributions, a random sample of 100 for each produces means that are significantly different, but medians that are not significantly different. The second reason is if you have a very small sample size. So if you don't meet the sample size guidelines for the parametric test and you are not confident that you have normally distributed data, you should use a non-parametric test. When you have a really small sample, you might not be able to ascertain the distribution of your data because the distribution test will lack sufficient power to provide meaningful results. So in this scenario, you're in a tough spot with no valid alternative. Non-parametric tests have less power to begin with, and it's a double whammy when you add small sample size on top of that. The third reason for using non-parametric tests is you have ordinal data, rank data, or outliers that you can't remove. Typical parametric tests can only assess continuous data, and the results can be significantly affected by outliers. Conversely, some non-parametric tests can handle ordinal, ranked data and not be seriously affected by outliers. So be sure to check the assumptions for the non-parametric test because each one has its own data requirements. So if you have Likert data in the future and you want to compare two groups, there would be different non-parametric tests applicable for that and parametric tests applicable for that. It depends on your sample size and all and other data requirements.